Hello, this is the lecture section 2.5, which is about continuity. So in this lecture, we'll see when a function is continuous, it means understand the continuity. Then we analyze some basic function using the concept of continuity. Okay. So roughly speaking, a continuous function is a function when we graph this function, we do this continuously. We don't stop. We don't need to stop and continue again. That means roughly speaking the continuity. In terms of mathematics, when or limits, when a function is continuous at a point A, that means when x approaches A, limit of f of x approaches the value of the function. Okay, and we will see exactly the definition, which is given here by definition 1. So a function f is continuous at A if the limit of f of x is equal to f of A. And here comes the difference compared to the limit, because for the limit we see that we need to compute right, left. If they meet, then the limit exists. Here for continuity, we have another condition. This limit must be the value of A of f at the point A. So we need to do a little bit more compared to the limit. If this condition limit of f of x is not equal to f of a is not satisfied, then we say that the function is continuous, discontinuous at the point A. Okay. So as we said, we have three conditions to be satisfied. First, f of a must be defined. The limit exists of f of x, and the limit is equal to f of a. So these three conditions ensure the continuity of f at the point A. If one of them is not satisfied, then we say that the function is discontinuous at the point A. We have three types of discontinuity. The first one that we call removable discontinuity if the limit exists. So one of the other two conditions is not satisfied. For example, we can think that f of a is not defined, or the limit is not equal to f of a. So removable discontinuity, that means we only have condition 2. Okay, if we have this and the other no, one of them is no, then this is removable. Okay. Now, the second type is the jump discontinuity. So for this case, we don't have the condition number 2. This is not satisfied, which means that limit right, limit left does not, they don't meet at the same point. The third one is infinite discontinuity. So if we have one of the limits to the right or to the left equal to minus infinity. Okay, so still we are in this condition which is not satisfied. Okay, so the limit is going to, sorry, not this one. We may have this condition not satisfied. So f of a is something, but the limit is somehow going to plus or minus infinity. So in any case, if the limit is plus minus infinity, this is infinite discontinuity. The function cannot be continuous at the point A. Okay. look at this example, we have several discontinuities. Now, think about we are graphing the function. So we start with the point at x equal to -3 here. You see, if we follow the graph, then I need here, since it is empty circle, I need to stop and continue. So this is discontinuity here. And what kind of discontinuity? This one, number one, is we have limit to the right, limit to the left. They meet at the same point, and the limit will be equal to this value, which is basically 1 here, I guess. Okay, this is, let's say this is 1 for any value, but the function is not defined. Okay, so we don't have any value for -2. So we call this removable discontinuity. Now we continue. If we continue with the graph, I need to stop here, then continue to the right. So this is also discontinuity. And what happens here? The limit is going to -infinity. So we say that this point, this discontinuity is infinite discontinuity. Good. Then we continue. I need to stop here and continue to the right. So this, again, this is discontinuity here at this point. And by the way, when we say discontinuity, we take the x. So here, the first one is x equal to -2, removable discontinuity. Here, x equal to -1. And here, x equal to 0, which is jump. Since we see that left, we are at this value, and the right, we are at this value. So there is a jump between right and left. So the limit does not exist here. Then we continue. And here I have to stop and continue the graph. So there is discontinuity at x equal to 1. And clearly, this is a jump since left to right. They don't meet, although the function is defined at the point 1, but doesn't matter for continuity. We need to have first limit to the right equal to limit to the left, and then it must be equal to the f of the value of the function. Now we continue to the end to finish the points of discontinuity. So in total, we have 1, 2, 3, and 4. Okay, now here is the solution. And now we continue with an example where we have the expression of the function, not the graph. So the question is to check the continuity of the given function at the indicated points. So here the checkpoints are, for the first one is a equal to 2, a equal to 0, and a equal to 2 for the third one. So here we want to satisfy the 3 conditions for the continuity. Limit to the right equal to the limit to the left equal to f of a. So for the first example, clearly we don't have f of a, f of 2. So f of 2 is not defined here. So this is discontinuity. 2 is the discontinuity for the function f. What type of discontinuity? We need to check the limit to the right, limit to the left. And since here the expression is the same for right and left, so I will check the limit at the point x approaches 2 of f of x. It means when I factor this polynomial, it's x minus 2 factor x plus 1 over x minus 2. So simplification, and then I substitute x with 2, so it will give 3. So I have the limit to the right and limit to the left. They both meet at the same point 3, but of course it's not equal to f of 2, which is not defined, so it's discontinuity. And here we find the type of discontinuity, so it's a removable discontinuity. Okay, now I will go to the second equation, second function, sorry. And the point is at 0. So here, f of 0 is defined. We have f of 0 equal to 1. That's fine. But we need to check for limit to the right and limit to the left for 0. So x approaches 0 plus is equal, this is f of x for 0 plus, and by the way, here 0 plus and 0 minus, we take the same expression, since x different than 0 contains the 0 plus and contains the 0 minus. So clearly here, when we put x approaches 0 plus, it's like 1 over 0 plus, so it's infinity. And same thing when we take 0 minus, it's also infinity since we have this squared here. So it makes the 0 minus will be like 0 plus. So here it's an infinite discontinuity, okay? The third one, again here f of 2 is defined, so it is equal to 1, okay? But we need to compute limit to the right, limit to the left of f of x. X approaches 2 plus, for example, okay? So my factoring here will be limit x minus 2 times x plus 1 over x minus 2. So, and by the way, this is the same for 2 plus and 2 minus, the same expression. So I could here remove this plus and work with 2 and see if I need to separate plus or minus. Here we simplify, so it's equal to 3. And this is different than f of 2, which is 1. So here, again, this is removable discontinuity. Good. Now, of course, here you have the solutions. And you have even the graphs of the functions. So clearly here it's removable. You see here is an infinite discontinuity. And again here removable, although the function is defined at 2. Let's see the definition number 2 for continuity. We say f is continuous from the right at A. We say we look to A to the right, so A plus. If we have, like the normal continuity, if we have limit of f of x when x approaches A plus, the only difference here that we take A plus. If we talk with the continuity from the left, we will take A minus. So we don't need to look to other side for continuity from the right or the left. And of course, we say the function is continuous at the point when it is continuous to the right and to the left. This is when the point is inside the interval, in the middle, inside the interval, not the endpoints. Okay, so here by this definition, we can use definition 3. We can define definition 3, which is the continuity on intervals. So when the interval is open like that, just take any point and you must have the continuity at any point inside AB open from both sides. However, when we take AB, close it at A, open at B. So in addition to the continuity at any point inside AB, we add the continuity to the right of A because A is closed. So I have to look to the right of A. So these, we're using definition number 2. And you understand if it is closed at B, the interval is closed at B, then in addition to the continuity in the open AB, you have to look to the continuity from the left at the point B. When it is closed from two sides, A and B, then in addition to the continuity inside the open set AB, you will take right continuity at A, left continuity at B. Look at this graph to make an application of the continuity. And here, there is a little thing to be considered here. When we say intervals, that means we will take one by one, not together, okay? The domain of continuity is something else. It will include all the domain of definition of the function, but here we will consider one interval separately, okay? So from this point till this one, till this one, we have here discontinuity. Let's talk about discontinuity first. So this discontinuity is at -2, -1, 0, 1, and that's it. These are the discontinuities. So if we take the first interval, it will be -3, -2, open. Okay, that's the first interval where the function is continuous at any point, including the continuity to the right for -3. Then the next one is -2, -2, 2, -1, open. The next one is -1 to 0, and here 0 closed if I consider just this region here, okay? Not all the domain. So clearly 0 is a discontinuity. We cannot talk about continuity at 0 if I look to the whole function. But in the interval -1, 0, this part is continuous. In fact, including the 0 from the left. Now, if I continue to the next interval, it will be 0 to 1. Although the function is defined at 1, but it is open here and we have a jump discontinuity. By the way, we could say something about the discontinuity. Let me finish the interval. So 0, 1, and the last one is 1, 2, 3, and 3 closed because this is the end point to the right. Okay, now this is removable. Okay, this discontinuity is infinite. This discontinuity is jump, and this one also jump. So 2 jumps discontinuity. Good. Let's continue now. Here are the solutions, of course. We have these rules for the continuity. If we have two functions f and g continuous at a, then the addition or subtraction or multiplication by a number and the multiplication of two functions are all continuous at the point A. So you start from f and g continuous at a point A, then the addition, difference, multiplication by constant, the f times g product is continuous at A. The only attention is for when f over g, then we have to pay attention that g of A must be not equal to 0. If we think about continuity on the whole interval, then the same rule will apply. Just be carefully to have g of x not equal to 0 because we need this division of f over g. Good. So by By definition 3 and theorem 1, we have, of course, some special case which are given here for the polynomial and for the rational function. So polynomial are continuous everywhere, and the rational function are continuous on their domain of definition because we have division. So we need to remove the zeros from the denominator. Look at this example. Determine the intervals of continuity of the function f of x equal to that. This is a rational function. So we need to make the denominator not equal to 0 to make the function defined. So not equal to 0, that means if we move f different than 3x and then x different than 5 over 3. So we need to remove this point. So it is, this function is continuous everywhere, okay, except the point 5 over 3. So we can say that r minus the point 5 over 3 that I can write in the following way, minus infinity 5 over 3 open, union 5 over 3 open, infinity. Okay. It turns out that most of the functions that you are familiar with are continuous on their domains of definition. So basically, you need to find the domain of definition to find the domain of continuity here for the function. Okay, so let's take a simple example here for sine and cosine and see what happens for the continuity at 0. Look at this, you remember this from semester 2. So if I take an angle theta, okay, I know that the point in the unit circle is of coordinates cosine theta, sine theta. If you remember here, this is the cosine and this is the sine. Okay, now this is for any theta, of course, it's the same. Now, if I make moving the theta towards 0 to get to approach 0, what happens? The point P will approach 1 and 0, and this makes two conclusions. Okay, the first one, that the cosine will approach 1. That's the limit of the cosine, and the sine will approach 0. So we conclude that when theta approaches 0, the cosine theta approaches 1 and the sine theta approaches 0. So we say that limit of cosine theta when theta approaches 0 is equal to 1, and limit of sine theta when theta approaches 0 is equal to 0. And so on, you do for the tan and the 6 other trigonometric functions. So here we have the conclusion, and we can do for tan the same thing. So if you want to get the limit of tan as x approaches 0, we know that sine will approach 0, and this will approach 1. So 0 over 1, by the theorem of division of two continuous functions, it will give the limit equal to 0. Here is the graph of tan, and clearly now we have this vertical, what we call vertical asymptote. If we are pi over 2 minus, then the graph is clearly going to plus infinity. But if we are pi over 2 plus, then the graph is going to minus infinity, and then we can conclude this limit for the tan. Also, we have clearly many infinite discontinuities at the point where we have the asymptote, like pi over 2, 3 pi over 2, and minus pi over 2, minus 3 pi over 2, and so on. in general, the most basic function are continuous, like polynomial, rational function, root function, trigonometric function, sine, cosine, tan, and so on. Inverse of trigonometric function like arctan, arcsine, arccosine on their domain of definition, of course. Exponential function, e of x, logarithmic function of all the type of any logarithmic type. Okay. Look at this example. We want to find the domain of continuity of the following function. So somehow, since we are dealing with the basic function, we will talk about the domain of definition of the function. If you find the domain, then that's the continuity, in fact. So what is the domain of f? Let's say x belongs to d of f, if and only if we have some condition to be satisfied. First, we have denominator. This must be not equal to 0. Okay, if we work to this means that x not equal to plus minus 1. We have to remove this. Also, we have something inside the tan minus 1. But this tan minus 1, domain of tan minus 1 is all real numbers. So no restriction for that. However, domain of ln is 0 infinity. So we must have x in 0 infinity. So look at this condition 1 and 2. Of course, we have to satisfy both of them. There is and. So we take the intersection of 1 and 2. So here I will find that domain of continuity, or by the way, as we said, domain of continuity is the same as domain of definition here. So it will be equal to 0 infinity. And we should remove normally plus minus 1. But since minus 1 is already out of 0 infinity, so we will remove 1. That we can write in the following way, 0, 1, union, 1, infinity. So that's the continuity of this function, domain of continuity of this function. Okay. Good. Theorem 4 says it's about continuity of a composite function, and this I will do it in the second part of this lecture.